Okay, so the Google Meet was really good this morning, guys, but the video didn't really work as planned, the recording at least, because it was just my face talking for 40 minutes. So what I'm going to do for you is just talk you through the content again, and I'll do it in the same format. Hopefully you'll be able to see the quality better with what we were talking through, and it should give you some notes to work from. So essentially what we're interested in is this idea around energy transfer. And we call this work done. Okay, and we can give an example of this. So we're going to take a very simple energy transfer in an appliance. So for example, a light bulb, and a light bulb converts electrical energy into light energy. But we obviously understand that this isn't the entire picture, because we understand that although light does come from the light bulb, there is also going to be some kind of waste from this process as well. Now we demonstrated energy transfer in the form of a Sankey diagram this week in the session. So let's just have a quick look at what one of these looks at, like for a light bulb. So what we do is we demonstrate the quantity of energy transfer by using the size of the arrow. So in this case, what we could do is we could have an arrow that's perhaps, say, that big. We'd measure this. So if this was 10 centimeters for 100 joules, and this was 7.5 centimeters for 75 joules, then we can work out the wasted energy. So there we'd have an arrow like so for 25 joules, and we understand that this is going to be the light, and this is going to be any kind of waste. So this could be any kind of sound or kind of heat that's coming from this and that is lost to the surroundings. Now what we are interested in this week is the fact that we can calculate the efficiency of this appliance and this energy transfer system. So we call this a system, where we have a very clear an input and an output just there, like so. Now the energy efficiency is equal to the useful energy out divided by the total energy in. Okay, so in this particular example, we'll show this in a different pen. The 100 joules is the energy in, and the 75 joules is the energy out. So 75 divided by 100, and then what we always do in this case is we times it by 100, and that gives us the calculation in the form of a percentage. So that particular system is 75% efficient. Okay, so that's where we started. Now what we need to be comfortable with is the fact that all processes and systems have useful output and wasted output. And what we should be comfortable with is that we are never ever going to find 100% efficiency. Okay. So what you need to be able to do is you need to be able to look at a system, and you need to be able to identify the useful and the wasted outputs. So if we look at a kettle has an input of electrical energy, and its useful in this case is going to be the heat that's put into the water, and the waste in this case is going to be any sound. You might get some infrared light from the filament, but also you have heat loss to the surroundings. So anything that loses heat to the surroundings is not putting the heat, in this case, into the useful output. The heat's going down into the surroundings and is not useful. Okay, so what we looked at this week is we looked at the idea of having heat engines, and heat engines work So if we take a heat engine, and we understand the idea that a heat engine has at one end a hot source, like so. So this could be a coal furnace with a boiler. It could be a hot cup of water that we looked at with our simple engine that we looked at, and we need a cold sink. Now a cold sink could be the air around the engine. It could be a tank of ice cold water. It doesn't really matter too much, but we understand that there is a temperature gradient, and we stick in the middle an engine, like so. Now according to the zeroth law of thermodynamics, heat will transfer from an area of high temp to an area of low temp. Okay, and this will happen until we reach what we call thermal equilibrium. And once we hit thermal equilibrium, that heat transfer will be equal in either direction. So heat, in this case, heat moves in that direction. Now there's different things we can measure on this engine here. Firstly, we can measure the temperature of that hot source. So T, and we can measure the temperature of that cold sink. So there T goes there. Okay, and we know that T is temperature. And we are going to measure temperature today in Kelvin, and I'll talk through this a little bit more in a minute. Now what we'll do is we'll understand that temperature, we should understand from the zeroth law, is that temperature is relative. So we're going to call this TH, and we're going to call this end TC. And these denote H as in hot and C as in cold. Hot, cold, I mean, hot could be 20 degrees, cold could be 4 degrees in comparison. But what you understand is that there's a gradient. So hot, cold, 20 to 4, there's a gradient. And what we understand at this point is that heat transfers. And heat, as we know, heat is denoted as Q. Okay, so Q will transfer along this system to the cold sink. Okay, now when we stick an engine in this system, the engine is capable of doing work. Okay, so W is work and Q is heat. Okay, so we've got all our letters in here denoted now, and what we need to be comfortable with at this point is that this is an input and this is an output. Okay, now what we tend to find is that the heat here will be high or hot, and here the heat will be cold or low. Okay, so H and C come into play here, and what we can also state as a result of this is that W, which is work, is equal to the heat in minus the heat out. So if we take this figure and this figure, we can calculate this figure. We can also, if we know this one and this one, we can calculate this one. And also, if we know this one and this one, we can calculate this one. So all of these three are relative to each other by that formula there. Now you won't be given this formula, but it should make sense to you as to what that formula means. Okay, so at this point, what we can also be comfortable with is that this can be reversed. Okay, so I'm just going to do this on the back of this sheet. So again, we can have hot source and a cold sink, like so. And we can stick something called a heat pump in the way, and a heat pump allows us to move the heat, or the heat and the energy, in the opposite direction. In order to achieve this, there's still work involved, but the work goes into the system. Okay, now the same principles apply in terms of temperature is high, temperature here is low or cold, and heat is still involved. What this allows you to do though is it allows you to extract heat from here and move it to here, and the same principles apply. Now what we understand at this point is that the efficiency of any system is limited by two factors. One is friction, so the more friction, the lower the efficiency, and two, heat loss to the surroundings. So if heat is being lost into the surroundings, it's not going into that system, so therefore it's lost. Now we can calculate efficiency in three ways. Firstly, we can calculate efficiency if we know the work done and we divide it by the hot heat. Two, we can calculate efficiency if we take the hot heat and minus away the cold heat and then divide the whole thing by the hot heat. Or three, we can work out efficiency if we do 1 minus the cold heat divided by the hot heat. Okay, now this one here is the one that you get on your formula sheet. So that's the one that you need to be able to use, but what we need to be comfortable with is that we can use any of these to get the answer to what we're trying to get to. Okay, and I'm going to demonstrate this now. If we take a hot source and a cold sink and we stick an engine in the middle, okay, and we're going to move heat in this direction, and we're going to try and work out how much work that engine is capable of doing, then we need to know a couple of things. Now firstly, we need to know how much energy goes in. So we're going to put 900 joules in, and coming out the other side is 300 joules. So you can see from 900 to 300 something has come out. Now the first thing we're going to calculate is work done. So work is equal to QH minus QC. This is 900 minus 300, which is 600 joules. Now the efficiency of this thing can be calculated, remember, in three ways. So one, we could do E equals W over QH. So that would be 600 divided by 900, and then we times by 100. Two, we can do E is equal to QH minus QC all over QH. So this would give us 900 minus 300 all over 900. And then again we need to times by 100. Or 3, we can do E equals 1 minus QC over QH. So this would be 1 minus 300 divided by 900 and then times 100. In either case, in any one of these, you will end up with the same answer. So it doesn't matter which way you do this, but this is the one that is given you to you on the formula sheet, and you need to be comfortable with using. Okay, but they all give you the same result. So not only have we calculated work done, we've also calculated efficiency. Potential for 2, 3, 4 marks in an exam in that situation, carrying your results forward. Now just to finish, we need to be comfortable with the idea that temperature can replace heat in any question, okay? And temperature needs to be measured in Kelvin or K, okay? Now, we know from our studies this week that 0 Kelvin, or absolute zero, is equal to minus 273.15 degrees Celsius. You need to learn that number. Okay, so learn that number there. Okay, you won't be given it necessarily in an exam. Now, if we're going to convert degrees Celsius into Kelvin, we basically need to add 273.15. Okay, so the example here, so 0 degrees Celsius will be 273.15 Kelvin. So you're just adding 273 onto that number there to get that figure. Now, where a question could come with this, so again, hot source, cold sink, engine in the middle, energy transfer, like so. It's not always possible to know the energy transferred from here to here to here to here. So what we might note down instead is we might know the temperature. So the temperature hot could be 250 degrees Celsius, and the temperature cold might be 40 degrees Celsius. Now in the exam they might give you these in Kelvin, in which case there's no need to convert, but they might not. So it's being ready to understand what they could get you to do here is try and get you to calculate the efficiency of an engine without telling you the Kelvin. So the first job that we need to do, and I'm just going to draw a line under that bit, so this is not relevant at the moment, is we're going to convert to Kelvin. Okay, so in this case TH is 250 plus our magic number of 273.15. okay, and this gives us 523.15 Kelvin. Our cold temperature is going to be 40 plus, again, our magic number, which is going to be 313.15 Kelvin. Okay, and now we're going to calculate the efficiency. Now to do this, we're going to need a new formula, and you are given this one in the exam. Okay, so the efficiency in this case is equal to 1 minus the cold temperature divided by the hot temperature. So, and then obviously times 100. So in this case, we take these numbers and we plug them in, and this gives us 1 minus 313.15 all over 523.15 times 100, and this gives us an efficiency of 40.14%. So this is applicable to some of the questions in the quiz. If you haven't already given a go, do look back over this. I'm hoping that talks you through the key content for today. So we should be comfortable firstly with what we mean by energy transfer in terms of work done, which was covered in that slide. We should be comfortable with efficiency being about wasted output. Here we're comfortable with what a heat engine is. Okay, so we've covered that idea around hot to cold. We can calculate the work done. We understand all of these denotations. We understand the zeroth law. From this, we talked about how efficiency is limited by friction and heat loss to the surroundings. We talked about the 3 ways to calculate efficiency, with this one being the really important one you need to use in the exam. We gave an example of that and we worked through it. What I would suggest is you just practice this. So this is using one of the formula sheet questions. This is another one that you're given on the formula sheet. We're learning this number here. So this is 273.15 to convert from degrees into Kelvin, and we're able to calculate the efficiency of an engine according to temperature. Any issues, drop me an email.